Good morning, Knowledge Graph Conference. How are you doing today? Good. Welcome to everyone here in New York, in this beautiful Cornell Tech campus, and to everyone watching on video around the world, welcome to you as well. So today what I want to do is really focus in on the modern data stack, where it started from, and then give an evolution of where it's going. The modern data stack is solving a huge number of analytic problems for thousands and thousands of companies. That has been thousands of companies have leveraged the technology of the modern data stack to really bring analytics forward, but they do see there's some places where there are challenges. And what I want to do is talk a little bit about those challenges, where they come in, and then talk about the road to knowledge graphs, and in particular where I think it's going, which is relational knowledge graphs. So let's look at the start of the modern data stack. The modern data stack was really born in that time frame, and it's evolved in some fundamental ways since then, and it's really broadly used across the industry. And the way I think it can be defined today in a very broad definition as really data analytics delivered as a service, a software service. So it's something you buy, you purchase the capability to run this as a service on the internet. It leverages the public cloud for scale and for low cost, and data is modeled for SQL. That's really important. It may be done in different ways. You might use Spark to do the modeling, but ultimately the data modeling that is done is predominantly around SQL to perform more rich analytics against it. So it's really about modeling, and it's about enabling you to set up the data so that it can be used by a SQL database and then used by things like BI tools. But what I want to do now is I really want to now talk about how people use the modern data stack and the different stages of the data stack. The modern data stack is really a closed loop today, and that's important. It didn't start this way, but it's evolving into a closed loop that begins with applications used by end users, and it goes through a series of steps: a data pipeline, a data warehouse, data lake, and I won't talk about the distinctions in that. Just I believe they're fundamentally coming together. Predictive analytics, and then a process called reverse ETL to take the data that's the analytic insights and put them back in applications. So it's a closed loop that begins and ends with applications used by people. And today we have 5 different data platforms that have evolved by large companies. They're delivering these services to, as I say, thousands and thousands of end users. And the interesting attribute of these companies is that if you look at where they began, they're all started from different places. Snowflake was the idea of a cloud data warehouse. BigQuery was Dremel. Amazon was the Toolbox plus Redshift. And of course, Databricks started with Spark. They all started in different places, but they're all converging to build a very similar solution for customers. And customers in the next few years will be able to choose any one of these platforms and believe they can get their jobs done. And that's really important because it means that there's huge industry choice out there. Now, the first stage of the modern data stack is the data pipeline. And data is created inside applications in many, many different forms. Certainly, we have SaaS applications creating data. We have in-house bespoke applications where the data originates in databases. Applications are throwing off huge amounts of semi-structured data and log data. There's images and video, all this rich sources of data that are being created by modern end-user applications. And data pipelines, of which there are many solutions, some of which are services like Matillion and Fivetran. Others are things you do yourself, like Python. But people are building pipelines to take that data out of the applications and put them in the cloud services where they can begin to perform analytics. And the important thing about this is that, as I say, people, as they're doing it, SQL is core to a lot of what they do, because SQL is used as the core way that you perform business analytics inside systems. And we have a wide variety of tools that are out there that have existed. It hasn't matured as fast as I might have thought it would, but there are quite a few tools that have been adopted by the industry. And the interesting observation I would have about business analytics and business BI is that when you're performing it, you need to understand business concepts that are not represented and modeled in SQL. So SQL is the de facto standard for data modeling, but it's not appropriate for business modeling, which is why you see things like LookML and DAX. It's why tools like Tableau use graphical approaches to model business concepts. That's just missing in SQL. And if we kind of go forward and we look towards a lot of the interesting stuff that's happening, it's all about machine learning, AI, predictive analytics, tons and tons of new tools and services emerging to support the interesting insights that can be done. And of course, I mean, this is kind of obvious, but predictive analytics are written in a procedural language like Python, not SQL. So people are working with a wide variety of tools to get their job done. It's actually pretty effective, this sort of approach. And yet there's a lot of different moving parts required to actually solve the problem. And if you look at what these 5 platforms are doing, they all started in a different place, but they're all converging, and they're all building a similar platform that contains both a modern SQL data warehouse together with a platform for building predictive analytics, often based off, generally always off the data frame, but often based off of Spark. And if you look across all 5 of these platforms, they're all doing similar things. They're all building these tools. They're all integrating them together. They're trying to provide an easier solution for customers to buy from them, even though today the best of breed involves different products from different companies, and most companies have stitched it together. Yet the industry is moving to make it better and easier for people to do this. And what are they trying to do? The goal of a lot of this is to create data applications. Data apps are apps that react to changes in the data and use analytic services to autonomously take action, to do something. Now, sometimes it's as simple as sending a Slack message or an email. Sometimes it can be changing the price of a ticket or doing a whole set of things that are really that take applications and take the modern predictive world and allow applications to move to a different place and solve a set of problems we could never solve before. But if we look at what people are building today, in today's world, almost all the data apps are a hybrid of queries against a SQL database together with procedural machine learning type code, some sort of advanced analytics written in Python or Scala or Julia or some other high-level language. And it's been pretty effective doing that. Now, the final stage that's evolved in the modern data stack is reverse ETL. And this is really focused on taking historical facts that exist typically inside the data warehouse, as well as predictions that are coming out of analytics, and putting them in applications that are used by people. And reverse ETL, it's a funny name. Some people don't like it, but it's not a horrible name. And what it really is an application integration solution. So that's the closed loop. It starts with apps used by people, and it ends with apps used by people. And what's emerged is an entire data stack that allows a whole new generation of these very, very important data apps to be built. Now, when we look at the modern data stack, and we look at what we can do effectively and what we can't do effectively, I would say the #1 problem that customers are having with all 5 of these platforms is governance. How do you govern and manage what turns out to be a pretty complicated environment? A lot of moving parts, multiple vendors in almost all cases. How do you manage that? How do you know what data you have? How do you ensure that the right people have access? Well, there are a set of concepts, a set of high-level capabilities that pretty much everyone needs. They need some kind of catalog for all their information. They need to do modeling. They need to understand what's happening in the data. And then they need to be able to protect it and make sure the right people have access. And then there are these high-level services. So here's a little bit of the details on some of these things. To me, a catalog is a simple inventory of assets. And Atlas is a pretty good solution. We're seeing Atlas emerge as a very commonly used solution by a number of these vendors. Modeling is a problem that today is largely being solved by dbt and tools of its ilk in the industry. And in a way, and in many ways, modeling has replaced the old master data management, which is really about homogenization of multiple sources of data into common formats and schema. But we need to model data, and we're doing that effectively in SQL, and we're transforming data effectively in SQL. That's working pretty well with tools. What we're not doing real well is business modeling. And the only thing people do today typically is ad hoc solutions, often embedded inside these BI tools that is a part of the solution. So business modeling is a big miss that is not solved, and it's very hard to solve some of these governance problems without doing some very explicit business modeling. Data observability and quality, we have a number of vendors that are in this space. You know, it does include things like what's the lineage, what are the data characteristics, what are the anomalous things that are coming across. But you know, I had a conversation recently with a large retail customer, and I had the most incredible insight listening to this data officer say, you know, and they said from their perspective, data quality was, does the data coming in follow the business rules of the company? They particularly said we do a lot of acquisitions, and we need to look at different data sources. Do they follow our business rules? That's a hard problem to solve. That's a hard problem to solve. Pretty hard to solve it if you haven't modeled things. And then there comes the data use and privacy. Oh my God, what a mess. Today, I mean, SQL role-based authentic authorization is king in the world, but it's the tools to manage that across these different systems really are relatively nascent. There are some products in the space, for sure, but we're not where we need to be. And there's tremendous, I mean, the amount of sensitive information that's being collected is important, and the ability to make sure that only the right people have access is absolutely critical. And then the high-level questions like compliance, legal, are we following GDPR policies correctly? I mean, we will see apps emerge to do that in the years ahead. Today, people have groups of attorneys and people figuring this stuff out, lots of humans doing all kinds of stuff. In the future, that'll be done through data apps, as it should be done. So standardized policies can be invoked across multiple companies within the same industry. So these are the sort of categories. If you went out and looked, you could probably find 50 vendors. I listed a few of them, and I kind of correlated to them the rough category that they say they focus on. But this is just a small subset. And my observation about this is it's a cacophony. If you look at every one of these vendors, they solve a set of problems, and there's a whole set of problems they don't solve, and there's no interoperability between these vendors, none. And why is that? Why is it that these products are built differently? The reason is they're not built on the modern data stack. Every single one of these tools has their own store associated with it. They have their own type of database. So there's no way these applications can interact. There is no standard platform. What's needed? What's missing? Well, governance apps are data apps. Let's just start with that. A governance app is a data app, and that's the way we should think about it. So what are the requirements for a data app in the world of the modern data stack? Delivered as a software service, leverages the public cloud for scale and low cost. That's right off the definition. And then the third one, reacts to changes in data and triggers business logic. That's a key characteristic of a data app. Maybe it's polling, maybe it's more sophisticated, but it still reacts to changes. Governance has some additional requirements. First of all, it has to be integrated into the modern data stack, obviously. But it has to have some more things. You need to be able to model business concepts, and you need to be able to support the highly complex relationships between those concepts. People talk about these as graph-oriented problems. So SQL databases and governance apps. SQL is not appropriate for building these applications. It's insufficient. It's not appropriate for business modeling, and it can't support the complexity of the relationships, the queries that need to be run. Why? Why is that? Why can't you use SQL for business modeling? The real answer is it wasn't designed to do that. I mean, it was designed originally, let's talk about SQL. It was designed in the 1970s, goes back to System R. It has been evolving through many committee changes over 40 years. How many, I mean, it's amazing. It's amazing how durable it has been and how people have used it, but it's meant, and it's meant to model tables and keys. That's what it does, not business relationships. So all of these things are problems. There are many, many more that you could potentially discuss, but the net of it is people recognize that we need more than SQL to do business modeling. But if you look at these databases, there's more to what's going on here than that. The relational algorithms that sit foundationally behind today's SQL databases cannot support the complex joins and relationships required in the graph-oriented problems that governance needs. And this is a data model I showed. It's a simplified data model of SQL role-based authorization. And you can see sort of in that ORM model that at the top, you've got a role hierarchy. So if you wanted to perform a query that say, hey, tell me all of the resources that Fred Jones has access to, all the data resources Fred Jones has access to in this organization, that's a hard query to write. In fact, it's a query that probably can't execute effectively on any modern SQL database if the organization is very large and complex. And the reason for that is because since System R, there has been a generation, many generations of algorithms built that have all been created around the idea of a binary join. They have two tables with a key, you join the two together, and then you get a result set, and the query optimizer takes and optimizes the order of those joins, and you binary join, binary join, binary join. These problems, these recursive problems, cannot be efficiently solved with those algorithms, period. You need different algorithms. And you know what? Snowflake, BigQuery, Redshift, Synapse, Oracle, SQL Server, DB2, System R, they're all based off the same, System R was awful early, but they're all based off similar sets of algorithmic design. So the industry knows this is a problem. They know this is a problem, and you see it everywhere. Our friends at DBT Labs, Tristan, he recently proposed this idea of a semantic layer. What a good idea, a semantic layer that sits above the modern data stack and solves some of these problems. It's really kind of a smart idea, and I think they're thinking in the right direction. But let's think about that. How would that look? Well, if you take Tristan's picture and you just shifted it to the picture I was using, I think it would look a little bit like this. You have the modern data stack, you have a semantic layer, and then you build, in this case, governance applications on top of that. But what the heck is a semantic layer? I don't know. So it's a semantic layer. Well, I argue that the knowledge graph fulfills the requirements of the governance semantic layer. So I listed the requirements, there they are, and I look at the Wikipedia definition of governance, of knowledge graph, and here's what it says. In knowledge representation and reasoning, knowledge graph is a knowledge base that uses a graph-structured data model or topology to integrate data. Knowledge graphs are often used to store interlinked descriptions of entities, objects, events, situations, or abstract concepts, while also encoding the semantics of the underlying used terminology. That's pretty good. It's pretty good. But it's not very concise. So let me give you a more concise definition of a knowledge graph that I hope becomes pretty useful for you. I hope this is useful. So a knowledge graph is a database. I don't know what a knowledge base is. SharePoint's a knowledge base, for God's sakes. A knowledge graph is a database. It needs transaction semantics associated with it that models business concepts, the relationships between them, and the associated business rules and constraints. Let me say that again. A knowledge graph is a database that models business concepts, the relationships between them, and the associated business rules and constraints. I think that's a pretty good definition, and it's very broad. It's very broad. That's important. So this is what it would look like. So if we put a knowledge graph system in as the semantic layer, We could put this here. And we could also use that knowledge graph to do more than governance. We could use it to build a new generation of these interesting data apps. Wouldn't that be interesting? So how do you build a knowledge graph system? Well, I've been building databases for 30 years. I mean, I've been working on this for a long time. I know of two ways to build a database. You can use navigational approaches, where there's some type of link or connections between the objects, or you can use relational approaches, where you have an algorithmic way of associating objects. And there is a difference between the what, which is declared in the query, and the how it's actually executed by the system. Now, I'm going to argue that for analytics, relational is the appropriate way to do it. And the reason I say this is because analytics are about the unknown. It's about the relationships we've never looked at before. And if you have to predefine a link for everything, how can you possibly do that? It's impossible to manage that, particularly in a world where these relationships the entities become so complex. There are literally hundreds or thousands or potentially even millions of relationships between objects in a large organization. How can you physically define connections between all of them? The most interesting ones are the ones you haven't even thought of yet. Relational techniques have won for a reason with SQL. It's because they solve that what-if problem so successfully, and they provide an effective abstraction for data. But there's a problem, because we already said that the algorithms that are built, that SQL databases use, are insufficient to solve this problem and won't work. So what we need to do is go back to fundamentals. Go back to the beginning and ask, what is the fundamental algorithmic capability of the relational technology? What can be done with it? And if we look back and we look to what Codd thought of back then, Codd had this theorem that he defined in the 1970s. And the theorem said that relational algebra and relational queries are precisely equivalent in expressive power. It's so interesting. I always knew this was interesting. Now I know why. And what that does is it allows us to separate the what from the how, and to express in a declarative way logic that is effectively what we need. It's complete for what we need to do. And if you look at what SQL databases are, SQL is a query language. It's a query language that goes through an optimizer, a query optimizer, that uses data to determine the right order to execute relational algebra statements. Well, if we move to relational knowledge graphs, we now go to the fundamentals of relational calculus, and we issue relational calculus statements that are unordered, okay, and they contain business rules and constraints. And the optimizer is now a semantic optimizer that optimizes not just data, but also the code. It makes decisions as to how to structure the results based on the code and the data. So it's a level smarter than today's query optimizers are. And we use data log-oriented approaches that express things in the form of fundamental logic. There exists, or for all x, such that expression. So that's the form of the queries. This work has been underway for a long time. I'll talk about that in a minute. It started in the early 2000s, and it really kicked off in about 2010. And it has been developed from many universities and many researchers around the world. It's done in cooperation. It's been an incredible cooperative effort among the research communities across the world. And a huge body, hundreds of papers have been built on this. A huge body of research has come out of new algorithms, brand new algorithms, that take different approaches to solving age-old problems, but fundamentally redefine how you can use relational algebra, relational calculus to solve these things. All of that work is fully published. So since we've been focusing on this in the 2010 timeframe, everything has been published. So there's no patents associated with it. What that means is that anyone can pick this up and use it. It's not open source. It's not done for you, but the foundational algorithms are there, and that's how SQL has always evolved, isn't it? You've had multiple companies building based on the same base of intellectual property, and in this case, it's available to all, and it's being used by a number of companies. Materialize uses it in a fundamental way inside the materializations that they perform. LinkedIn adopted some of this through a database, a graph database they use called Liquid. And this work was really pioneered by Mohan Maraf, who's here in the room today, and the RelationalAI team, again, in conjunction with literally with almost 24 researchers around the world. So what is it? So the RelationalAI knowledge graph system is a product, it's a service where business concepts are expressed using fully normalized relational data model. We call this graph normal form. Data is stored as base relations. So everything is a relation. And if everything is a relation, you better be able to do a lot of joins. So with these new algorithms, we can fearlessly do dozens or even hundreds of joins to solve very, very complicated graph solutions. So new algorithms that enable that through multi-way joins. It's fascinating. In the old world with binary joins, more joins slow you down. In the new world with multi-way joins, more joins speed you up because they can create constraints. Isn't it crazy that we do those binary joins today when we have all that memory available? Remember, when System R did that, they were working with like 8K of memory. That's where that all came from. And here we are today, still doing binary joins 40 years later when we have gigabytes and gigabytes of memory available. A new language, we call it REL. It's a declarative language. It's based on data log. It supports the full relational calculus plus recursion. So within the domain of what you're working on, you have the full expressibility of everything you need to do to build these data apps. So it's everything you need. And in this world, business rules and constraints are written as declarative, unordered declarative statements that are associated with the data, and they are executed by the query optimizer, or the semantic optimizer, which I'll mention here. So the semantic optimizer takes the relations, and it takes the business rules and constraints, and based on the query that it's running or the work that it's doing, it decides what code needs to execute in what order. As I say, it semantically optimizes not just the data in the query, but the code. Again, a whole new basis of research work around semantic optimization, which enables this and makes it possible. SQL remains important. SQL is not going away. In fact, I can even argue that the best days of SQL are ahead of it. I can even make that argument, that more SQL will get written in the future than in the past. I'm sure that's a true statement, certain of that statement. So it's not going away anytime soon. But as we said, it's insufficient. We need to have it to help bridge people into this world. Even with all of its problems, like nulls and everything else, still, we need to have it. And then very, very important in this is the transaction model. As I say, it needs to be a database. A knowledge graph needs to be a database. It needs to have transaction semantics. And in the transaction semantics now, we need to fully transact the model, the data, and the code. A lot of SQL databases don't transact the model. They certainly don't transact the code. We need to transact all three. What an interesting developer model when you can put all of those three things together in a single logical transaction that is immutable and historical and versioned. Amazing, amazing potential from a perspective of software development, and all kinds of things come from this. In this world, we get, for the first time, to where we can begin to see the model as not just something we put up on a whiteboard that an engineer needs to look at to write some Java code against. But now the model becomes executable. It can become the actual program. Here's a different view of it, the system. So relational knowledge graph system that supports both SQL and REL. Wide variety of different apps can be supported, governance apps, data apps. DSLs are interesting. I'm not certain how important DSLs are going to be in the future. I see a huge emergence of low code, these really interesting DSLs all over the place. We think supporting those are interesting. Turns out that a relational knowledge graph is a very, very effective data structure to support most DSLs in. And an interesting piece of work we've done recently, a little prototype got done with our friends at Goldman Sachs, between RAI and Goldman Sachs, where they have a very rich, really amazing financial services DSL they call Legend, that they've used to model Goldman Sachs's business. And in fact, it's open, it's open, and other financial services are using it as well. And Legend maps to different kinds of backend systems. And we did the prototype of mapping Legend to Rel, and it is a really great match. This approach is actually very generalized. And as the technology matures, and I want to focus on the fact that it is not yet mature, but as the technology matures, we're going to see things we can do with it that we couldn't even dream of. So DSLs will be important, and we see some interesting cases. And as I said, SQL is important. And SQL is how you get support for Tableau and other things like that. It's been a long time coming. This is not something that just started yesterday. It's really been almost a 20-year project. It's really got going in a big way in 2010 when Mulhem helped to drive a data log workshop at Oxford. And that really started this cross-university research contribution. I'm amazed by that work. I'm just blown away by the incredible work that brilliant people have done to create new approaches to solving problems that are going to revolutionize the industry for sure. So it's been a long journey with lots and lots of people contributing their brilliance to this. And it's a long product journey. I mean, Mulhem has built a couple of companies. A lot of great ideas came out of logic blocks. A lot of this work came out of that. And RelationalAI was founded in 2017. It's not yesterday, but it's still early. It's still early, and there's still a lot of work to do. This is not done. This is not done. But it's going to matter. It's going to matter in massive ways. Where we are now is we have a really functional system, and people are using it. People are using it successfully. We have some production use. It's pretty white glove, but we have some production use. We have a number of organizations we're doing limited trials with. That's where we'll be all this year, in a limited form, very much friends and family, because we really don't have the capacity to support broad sets of customers. Starting next year, it's our expectation that we'll open it up for self-service and have a broad developer beta so people can sign up and begin to use the system. And then we'll watch over time as the system matures and as people use it, and we'll authorize production on these things over time. Eventually, everything will be production. This is a very similar process to what I recall we went through at Snowflake. I joined Snowflake in 2014. And we wound up doing general availability about a year afterwards. And there was a lot of work between when I joined to when we were able to say it was generally available for production. We're still at that state with relational AI, but it's coming. It's coming. So the problems this solves are pretty interesting. It broadens what people can do with analytics to solving a whole new set of workloads and problems that you can't solve with the modern data stack. Modern data stack is great for data warehousing and data engineering, and things like Snowflake have done amazing things with data sharing. People are building data science on Spark. People are building these data apps, although they're building them the wrong way, in my opinion. And they're being successful, but it's sort of where we are. It's state of the art currently, but the state of the art changes. With this technology, with relational knowledge graphs, we have whole new workloads, graph analytics, reasoning, mathematical optimization, and my most interesting favorite, which is relational machine learning. I don't know where that's going to take us, but I'm sure it's going to take us places we haven't dreamed of yet. And so it's exciting to see that as this technology emerges, these new things can be done with it. So here we are. Here we are at the Knowledge Graph Conference. It's just the beginning. We're at the start of a whole new era. It's like the modern data stack in 2013, 2014. It's where it is, where we are in that life cycle. And just like the modern data stack has revolutionized analytics, I'm completely convinced that knowledge graphs, in particular relational knowledge graphs, are going to transform the way business runs. You know, in the early 1980s, a friend of mine that I worked with, he was my boss at the time, he's still a personal friend of ours, he introduced me to business modeling and the tools from INRIX that supported that back then. And we did some business modeling of what we were doing. And it was pretty cool. And it wrote a bunch of COBOL code. That's what it did. And the idea back then was that models would be written and it would write COBOL code. It didn't work. It didn't work at all because the semantics weren't fully expressible in that. And so, of course, the COBOL code was unmaintainable. And basically, modeling has become a whiteboard exercise. That's going to change. That's going to completely change. With this technology, you get executable models. The model becomes the program. And so business analysts can begin to interact and actually make changes to the analytics and the data structure. Think about that. Think about the potential of having 10 times as many people have access that are knowledgeable about the business, be able to affect the business. Think about the potential that has to the industry. That's the future of relational knowledge graphs. That's the future. That's why this conference is here. It's a pretty cool future. Thank you very much. I'm glad to be here.